So Rafael, yeah, thank you very much. So hello everyone, my name is Yongguk Jung. I'm the part of the Industrial Transformation Platform from KTH, and welcome to the last Sustainable Transformation seminars of this year. Today we have a speaker from Eindhoven University of Technology, Pavlo Bazilinskyy. He's an assistant professor at TU Eindhoven, and he's focusing on AI-driven interaction between autonomous vehicles and other road users like pedestrians and bicycles. And he finished his PhD at the TU Delft, and also he is also a member of Marie Curie Fellow as well, and when he was doing the postdoc. And I saw that you also work as a industry, as a data scientist. So that's an interesting background, but he will introduce himself more in detail. So welcome, Pablo, and please start your seminar.
Thank you so much for invitation and introduction. I will now start my screen to share my screen. Just to check, you guys can see it now?
Yep, we can see your screen.
Okay.
Not yet in the presentation mode. Yeah.
Okay.
Now we can see it. Yeah.
So hello. Thank you so much for your invitation again. So my name is Pavlo, and then I will now say a few words about myself also. And then we'll discuss the topic of multi-agent human factors research in automotive. After saying a few words of myself, so I basically try to introduce why people like me bother with looking into this issue of multi-agent human factors research in automotive. And then I will say a few words, and I will show you a few slides, these graphs, just more like an example of what's possible with this kind of technique of multi-agent research, about two studies which were done with one simulator, which I was working on in my years in Delft. And then I'll also share a few thoughts for future. So who am I? So as was said just before a bit, but I will say it in a very few words. I'm from Ukraine. My background is mostly computer science with a twist of IT, and I actually did my bachelor's not too far from you. I was in Finland in Eindhoven University of Applied Sciences, but then I traveled around a bit. So I was a Erasmus Mundus student in Ireland and Scotland, where I focused on AI. But then at some point I was a bit bored with doing compiler optimization for my projects, and I looked for a more applied and perhaps actually useful for the future and sustainable future topic. And that brought me to TU Delft in the Netherlands, where I did a PhD in the question of how automated driving can be implemented with the twist of actually taking a human into the account. So it was about human factors. And then I worked as a data science researcher in a startup in the Netherlands. And then I also did a postdoc in Delft. And at the moment, I'm in Eindhoven, the TU Eindhoven in the southeast of the Netherlands, where I'm assistant professor looking into AI-driven interaction between humans. These days, mostly outside of the vehicle. In my PhD, it was mostly about inside of the car and such cars of different levels of automation. So a bit of a backstory. So since it's in this interdisciplinary kind of presentation, I will try to be also a little bit generic in my what I will say. And the grand scheme of things is that a lot of people die in traffic every year. So the Netherlands, Sweden are safe enough. Sweden maybe even a front runner in the world when it gets to safety. However, still the number of people who die, unfortunately, is increasing. And 95% of these deaths are caused by the human factor. There are a couple of examples. One of them are quite sad. So people now use social media and Instagram themselves. So you saw in this video, so this video, it unfortunately often causes accidents and death, like that, which is very sad. But essentially, a lot of these people who die are vulnerable road users, as I say. So these are people who are vulnerable outside of the car, such as pedestrians, cyclists, motorcyclists, as well as drivers. And the theory is that if you actually remove the human from the equation, so in practice and in theory, perhaps 95% of deaths out of that 1+ million people could be avoided. And that also comes with a lot of benefits as well in a framework of sustainability. So when traffic is a lot less dense, with automatic cars around, some models say that we will need 10 times fewer cars than we need today, because even the whole concept of private vehicle may go away, because you can always just tell your car to drive away and then come back to you when you need it. And also parking takes a lot of space in the Netherlands, less so maybe in Sweden, but in the Netherlands it's a big issue. There's not so much space here. And as a result, city councils, for example, invest a lot of funds into the research of how automated cars could be put into practice, because that also comes with a side effect of essentially parking lots being freed, and the parking lots could then be turned into parks. And then we all want to have better air around us to breathe. And then when you have fewer cars as a result, also a lot more emissions are given into the air, and then the whole world actually becomes cleaner. So this is at least my view, and then many of my colleagues, and that's kind of why I'm doing this. I actually believe that automated driving could be quite a good thing in the world in the future. And in more detail, so my niche, when it gets to the problem of automated driving, my niche is how cars and humans interact. So I do not make sensors. I do not create algorithms so much. Instead, I use what has been done in places like Eindhoven, Delft, and perhaps KTH. And then we and my colleagues then try to see how that technology can be then applied when the car is next to you, and you being, for example, a pedestrian in this case. So this is a good example of my PhD research, where a car perhaps would stop next to you. I think that's a video. Yeah. So it will come to you as a pedestrian, for example. Maybe there is, like, if you see a beer sign blinking, so there's some distractions. And then since in the future, there is no driver in the car by definition, we need to find a way for the car and the human to interact. One of such ways could be, for example, a visual message. And then in years of my PhD research, I focused a lot on how such a message could be shown to you. In this case, which was shown in the paper linked in the bottom, by the way, you will see that in this case, the car shows you a message will stop in green color. Then the other questions pop up: why it should be green, why there should be a text message in the first place, maybe it should be like a smiley face, which is also was shown to work well. And that was nice, but then I did a lot of research about how that specific phrase message should be done. And I will not go into that, but you can check also if you're bored some of my older papers. But that also brought me into thinking of actually that actually in the real world, situations are way more complicated. In the real world, instead of one car, one pedestrian, for the most part, you will have multiple cars, multiple pedestrians. And in the future world, you may see yourself in a street where many cars are automated. Perhaps it's a world with mixed traffic where some other cars are still manual. And you are a pedestrian, like in this diagram, you may see yourself as, in this case, a skeleton on the left trying to cross. And then there could be a car which says don't walk, but then there could be another car which ignores this message. So that brought me into thinking of something complicated. And this is the heavy slide, so bear with me for a second. I will not go too much into detail, but essentially this is kind of the main result of my PhD, where I tried to explain how I see, it's my vision of how I see things will be in the future, a sustainable, perhaps transformed future, where one of the key elements could be that we may have vehicle to everything communication. So V2X concept is quite popular these days, where we assume that actually everything's connected. So if you have multiple automated vehicles, multiple pedestrians, one of the ideas these days is that more or less everyone will know everything about everyone else. And in that framework, you may imagine yourself having multiple cars, such as automated vehicles, which have multiple drivers, well, one driver, in this case, a passenger, and a multiple passengers. And then all of them maybe doing different things. So they can be doing non-driving tasks. So in the future, when you're in the car, by definition, you may do something else. So for example, you can watch a Harry Potter movie in your car while they're driving. Then these people may have the gaze. So maybe you're watching the movie, but sometimes you also gaze outside. And outside are still people. They're the vulnerable road users in this case, as I said a few slides before. And I looked into specific cases of pedestrians or cyclists where multiple of them could be around you. And as well, they may exhibit gaze, so they can look back into you if you're inside of the car. They can be moving, so there's movement as well, and just a behavior. And then all these lines essentially represent a schematic way of how things interact. So a car can have an external human-machine interface, which I will now touch upon in the next examples, which is essentially the message you showed, which you saw a few slides back of wheel walk. It's an external interface. And then the car can have indeed sensors, which can detect what others are doing. And then the vehicle dynamics of the car, so the car moves in different ways, is also what the pedestrians and cyclists can base their decisions upon. And obviously the car will have control logic and AI, which controls the whole thing. Essentially, this slide is here to tell you my message that things are quite complicated, and they are a lot more complicated in the real world situation where multiple agents are interacting with each other. And I understood that that's basically essentially the way things are when I was in my PhD a few years ago. But then I started looking for a tool to allow me to expand my research questions onto the multiple agents situations, multiple cars, multiple vulnerable road users. I discovered that there are a few simulators out there, but unless I was willing to pay a few million euros and get a closed source system, it was a bit hard for me to actually understand what I wanted to do. And then I decided, why shouldn't I make my own simulator? So that's what I did. And since I've always been a big advocate of open science and open data, I essentially made an open source simulator, which you can, if you're curious, you can see it in the GitHub repository in the bottom, where I use only free assets. So if you use the simulator, whatever you do with it, you can always publish it anywhere you want without any strings attached. And my philosophy was that if the asset for free doesn't exist, I will make one, or I even outsource some of development to people who are professionals. Also, it's by the way, one of the things which I brought into my research. I did a lot of freelance outsourcing. Essentially, my idea was that, yes, I was doing this work as a PhD student, but there's somebody else in the world who is way more qualified than me, for example, in Unity development. And instead of me spending 1 year on doing that, I would rather focus my year on more conceptual research questions, and then I will outsource some of it to a professional. That's what I did, which is also a bit controversial, but it worked out quite well in my case. And then the main idea of this is that we basically made, now I will show you a game, a Unity game, but with science-grade data recording level. So it's a game which allows you to connect unlimited number of agents, human and automated agents together. But we did a binary level data acquisition network layer, which works at about 100 hertz, which allows you to detect quite fine details of how humans behave. And humans are complicated, which I tried to show in a demo. So this is now a simulator, and it's me and a few of my colleagues from Delft. I'm on the right side, and I'm now, in this case, walking in a motion suit. So my movements are given to the world real time from 25 IMUs. And then my colleagues, for the purpose of the demo, one of them was in the automated car with a message walk. Another guy was in the car. And now you can see I followed the message walk and I was crossing the street, but the other guy in the car, in the manual car, ignored the message. And it's an example of a conflict situation in a mixed traffic case where one car may show you one message, but the other car may ignore it. And then the human pedestrian can then follow the first message, and that could lead to a fatal accident. And just a demo. Again, this simulator is on GitHub, so if you are curious, you can check it out. And now I will spend most of my remaining time on giving you some brief introduction to two use cases of how it was done, how we used the simulator to understand how multiple humans and automated vehicles could live together in the future. First one is called stopping by looking, and essentially that's exactly what it says, where we use two eye trackers connected. I think it's video as well. Oh, no, not video, but okay. And then we had two eye trackers connected. We invited groups of two persons to join our experiment, where they wore the eye tracker with called Vario 2 Pro, which has it's a head-mount display with virtual reality display. This eye tracker integrated. It was Toby, so a Swedish actually device. And then in this case, we had a car and a second car, which was for destruction. And we asked our people, our pedestrians, to be in our experiment with eye trackers. One of them was a driver of an automated vehicle. Second participant was a pedestrian trying to cross the street in front of such a car. And then what happened was we had three conditions. One was a baseline. So the automated vehicle was pre-programmed to yield, to let go, let the pedestrian cross or not yield. And then there are two things which were interesting. So first was look to yield, LTY as we called it, condition where the vehicle stopped in front of a pedestrian if they looked at each other. And looking at each other was is implemented real time. So essentially when two eye trackers looked at each other, the simulator understood it, so the two vectors aligned, and then that was seen as a eye contact detected. And then in LTY, like look to yield situation, when the eye contact was there, the car stopped. And in the look away to yield situation, so the car yielded when the driver did not look at the pedestrian. Essentially, we in this case, we thought, why shouldn't we use eye gaze in the first place as a medium of communication in the future, where drivers, for example, are looking away, so the eye contact and hand gestures, which have been used today a lot, in the future, they may not be there. Specifically, it looked a bit like this. So that's now a small demo of what happened. You would have two agents in this case. By the way, the simulator has been updated quite a bit since then, so it looks a bit better now than here. But what happened then was a car would drive. And then on the left side, you can see the vectors of the eye gaze. And when they align, they would be basically eye contact. And the pedestrian had also a button to press. So when they pressed the button, it meant they are willing to cross. When they did not press the button, it indicated that they were not willing to cross. So it's a binary situation going on there. And then we plotted the distance to the pedestrian. And what it meant is shown a bit in this case. So now it's another heavy slide. Apologies for that, but I will go through it a bit. Again, look at the paper if you want to know a bit more details, but since it's an interdisciplinary audience today, I will just touch upon the main points of what we saw in the study. So first of all, it worked. So it was done quite some years ago, 3 or 4 years ago, and then it was one of the first basic studies in the world where we looked into multiple humans interacting with each other in the context of traffic and automated driving. And in this specific showcase of the data which we got, you can see that you can see the driver's gaze on these graphs. Essentially, on the x-axis, you will see the gaze, the angle of the gaze of a driver where they looked. And then it's a histogram. So on the y-axis, you see the frequency of that occurrence in terms of degrees. And on the left side, you see the situations when the car yielded with second vehicle. So as you remember, there was a car as well on the other side of the street, which was destruction. So we also tried to see how this kind of eye contact translates onto a real life situation as is a destruction present. And the right side was without the second vehicle. And then left side shows yielding situations when the car yielded, and the left side on the right side is not yielding. Basically, on the left side, you see that the look to yield case was a bit more to the right. So the driver looked at the pedestrian, which was on the right. And the left side, essentially, you see that's reversed. So it's more on the left. So it's flipped. Red is on the left and yellow is on the right. And the other way is yellow on the left and red on the right. So without the second vehicle, the driver looked more in the center and left. So essentially, it means that actually it works. If you have eye contact present, which I will now try to describe a bit more. If you have eye contact present, you could use it to indicate that to the pedestrian that, hey, he can cross the street because there's a car in front of you. This graph is a bit of another example of what kind of data we got from this multi-agent situation. It's a key press performance of the pedestrians. So they press the key to indicate if they wanted to cross or not. And in this case, you see that there are quite a bit of difference between the lines. And again, red means look to yield and yellow is look away to yield. And solid lines are the yielding situations when the car stopped, and the dotted lines are the non-yielding situation when the car continued. You can see that in case of the yielding situation, the baseline is quite a bit lower. So it means that the mean willingness to cross in case of baseline, so not all eye contact used, was lower than when eye contact was used. So essentially, it means that in the future, when there are cars with driver which looks at you and you may use eye contact as medium of communication, it is more beneficial to provide safe space to cross than not use eye contact. So what it all means? Well, in the first place, we wanted to see in general if eye contact could actually be used as a medium of communication, which is a bit of out of the box kind of thinking, and we were curious if it worked, and it actually worked. So the LTY look to yield mapping achieved higher acceptance rating than the look away to yield, and in general, both of them worked better in this framework than the baseline condition. And then the insights of the study may be important for the future maneuver-based control of automated vehicles. We don't know yet what happens in the future, 20, 40, 50 years from now. Maybe actually suddenly we'll realize that such a medium of communication as eyes being used could be actually useful. And then the results for potential for the communication of driver's intent by addressing the pedestrian directly with the augmented feedback. Okay, I'm running a bit behind the schedule, so I'm also sorry for going too fast. But again, maybe we can discuss some things after, and then you can always see the papers which are linked in the QR codes, and I guess you'll get the slides later. Now I will show you a few more graphs, and I will show you some nice videos and pictures from this study, where it's called "Get Out of the Way." And this it was actually a bachelor group study in Delft, where we examined how EHMI, so the messages in front of the car, if they're effective in case of critical maneuvers. So most research today is focused on safe sterile environments where there's a pedestrian crossing in a very safe environment. But in my view, such EHMI, so messages on the automated car, may be of most benefit in situations when there is actual threat to the life of, for example, a pedestrian. So it's evasive maneuver is one of such cases where if you're a pedestrian, situation is such that you need to evade being killed. And we modeled it in two scenarios. One was scenario one, where there's a car with an EHMI, so like little smart vehicle with a display, which would then show you an arrow right or left, trying to show you as a pedestrian how to evade a possible collision, because there was another car, distraction car. So we tried to distract the driver from seeing the automated vehicle coming fast. And the second scenario was similar, but then we also added a truck. So then when the car was driving, so it was kind of a corner, and then the car had to, basically the car turned, and then there was a pedestrian suddenly. So the participants of the study, also a couple of, in each case, were not aware that there would be such a collision happening. And then there was also even a truck. So then the field of view of the driver was obstructed. And well, like in the first scenario, the car wouldn't show you going left or right to indicate where you need to basically jump away from the trajectory of the car. again, so it was done in the couple simulator. And then for the purposes of making things synchronized, because there was a human involved, so it's hard to control the human behavior, we gave this display to tell to the pedestrian participant when they need to cross. And this was timed real time by means of this couple simulator to basically location the car to make the timing right so that the collision was unavoidable. Unless the pedestrian jumped away, which is what we tried to model. By the way, so for example, this evasive maneuver is quite hard to research in real life. That's maybe I should have said it before 10 minutes ago. This is why we're doing this couple of research, because some situations involving cars are just not possible to test in real life with real cars and real humans. That's why it's useful to use such simulators. And then what was happening is a bit like this. So the car drove on the right, and then depending on the rectangle of the car coming to the zebra crossing, the message will be shown left or right. And then the pedestrian will be walking on the zebra crossing. And then they used a lot this metric of the pedestrian distance, pedestrian location within the zebra crossing. So we called it Y coordinate. And then what happened was a bit like this. Actually, it's a video. So essentially, you will now see that the participants were quite immersed. So the guy on the right, the pedestrian, so he is now standing there. Now he will see the green. So now he will start walking, and then suddenly there's a car, and then he would jump out. This is a bit of a safe demo, but in some cases people really jumped. People really like try to escape the collision. And now he stepped back from the car. So what it all means in numbers, again, a bit of a complicated graph, but if you, in case you are actually interested in this topic in more detail, you can see the paper. But now a bit of a demo of how things work in this kind of multi-agent simulation. On this slide, you see the Y coordinate of the pedestrian in 4 conditions. So it's a matrix of HMI, so the message on the car on off, and also scenario 1 and 2. If you remember the slide of the zebra, so Y coordinate is the location of the pedestrian within the zebra crossing. And then it essentially shows you a few things. So first of all, is that the experiment actually worked. So it successfully created the critical encounters with the collision pedestrian crossing before the driver, so magenta markers. So this means that the pedestrian remained at the moment of possible collision. The pedestrian remained before the car, and the blue means the pedestrian was behind the car, so behind the vehicle. You may see that with the HMI on, some lines after, so this is the moment of collision, so some lines go down, so there's negative slope. What that shows you is that some pedestrians walk back. So when EHMI was there, so the message on the car was present, it worked, because unlike the EHMI off situation, so pedestrian had more information in the head to make a decision of trying to avoid the car. A bit similar situation. So now this figure shows the driver data position as a function of time. So it's a driver position on the y-axis, and over time, again, same time of occurrence. So around this second, that would be the main moment of collision. And then drivers often steer to the right onto the sidewalk as well, signified by negative y coordinates. So then in this case, if the driver situation was negative, so 0 is essentially the end of the lane of the road. If it goes negative, so the driver tried to avoid the condition in such a way that they even drove onto the sidewalk. It can also be seen that the driver sometimes steered onto the left side as well, which is in the cases of the y coordinate of more than 10 meters. A little bit in more simpler terms, now you see this graph. So it illustrates, this figure illustrates drivers mostly evade each other, because it shows you, again, the scenarios 1, 2, and HMI on and off. And now show the difference between the pedestrian and the center of the y coordinate and the center of the car. at the moment of contact. And essentially, if you look at the things between dotted lines, which is 2 meters, that would be the width of the car. And if the markers are there, it means that the coordinate of the pedestrian and the car were aligned, which means a crash. So in some cases, there was a crash, which still happened. I will not go too much into detail, but with some significance, we show that actually with HMI on, the number of crashes is lower. So HMI, again, it worked in this critical situation. To wrap up a bit, so for this study, what we concluded is that HMI's external such displays may have some value in the situations when pedestrians were found to be responsive to the HMIs. So HMI did not prevent, however, in statistically significant manner, but it was close. I think with some more with some more careful design, we could have made this study a little bit more conclusive. Future work, and we argue, me and my colleagues, that EHMI, such external messages, may actually be most useful in critical situations, which then also premises to discuss such research in the future instead of more sterile, very safe conditions. And just one more slide from me. What does it all mean? It's a bit like my general philosophy in research and why I'm doing what I'm doing. I think that who controls data controls the world. It's not, it's Albert Einstein, not quote, but I think that's a kind of a ground truth a bit of where we live in today, especially in the past months. I think it's becoming more and more apparent. And also, I work in the field of human factors, which is an old field. It comes from aerospace, and people in my field are used to making experiments with 1 millimeter advances, which is fair because you often deal with safety critical systems. So if you make a mistake, people die, and that's not good. But suddenly, I think we find ourselves in the world of enabling technologies. So this kind of couple simulator, which is done in Unity and is hosted on GitHub, and I use Heroku application hosting to do some experiments, crowdsourced, and I use freelance and outsourcing. I store my data in some Mongo database online. We now live in such a world where such research suddenly is not that hard. So 40 years ago, it was way harder to discuss this kind of multi-agent situations, but now it's much easier. We also have sensors around us like Jetson Nano, which are used in some other research. And I think it's basically time to step up to more realistic scenarios, especially in this kind of automated driving paradigm. And I think many cognitive theories need to be updated. So there are multiple theories in my field where people try to discuss how humans interact, how humans work when there are cars around. And I think those are quite outdated. I think a little bit went over time, but thanks a lot for your attention. And I hope it was useful. Maybe there are some questions. I will now stop my screen.
Thank you very much. Thank you very much. It was very interesting topic. So maybe we can collect some questions if there is any question from the audience. And maybe, do you want? Yeah, we have a question here.
Hey, Pavlo, thank you for a so interesting presentation. I wasn't aware of all the advances that are being made for avoiding deaths and for the safety of pedestrians and passengers. One of the things that I was wondering is whether in these experiments it matters the population, the composition of the population or the subjects, because I suppose that for example, different ages or maybe the genders or the ages matter. Could you give us some insights into this perspective, perhaps?
Very good question. Maybe I'll share my screen again. Just it's a very good question, which also is a lot in my mind. And I will now spend a bit about my own research and what I do. But if you look at my publications, which are by the way on my website, all of them are open source. I mean, open data and open science and all that, so you can see all of them there. I use a lot of crowdsourcing. So actually, like a lot of my research is deals with exactly that issue. That in most research today, we have 12, 15 male white participants from a highly educated background. And in my case, I think that we make cars, especially for the whole world. As a result, I often go with, for example, in this case, 1,200 people from all over the world crowdsourced. And essentially, that's how I also try to achieve more higher level of data power in terms of distribution of ages and genders and backgrounds, especially. And I think I even here, somewhere here, I even describe it my philosophy in my website, so you can also, if you're bored, you can check. But indeed, what is said is true, and I'm strongly against this kind of more limited data samples, and that's why I'm also trying to achieve in my field. In these two, just follow up, in these two experiments, indeed, there were more controlled laboratory setting experiments, because we had this coupled eye tracking involved and so on. But actually, at the moment, I'm running a study crowdsourced as well, where we use JavaScript eye tracker. So even eye tracking today can be done over the cloud. And we are now collecting data sample to 1,000 people from all over the world, interacting with some concepts from our research, trying to see also how that works.
Yep. Oh, we got a question from Osa. The question is how to accommodate for people with physical and mental disabilities. That's also relevant.
That is
question, I guess.
that is a very relevant question as well. Thank you, Asa. There are a whole series of grants and projects on exactly that. In the Netherlands, especially, I think it's quite prominent in that field. I'm involved in some of them. It is an interesting issue, and then also we are basically trying to see that. So, for example, textual HMI, which I showed in one of the first slides. Then a logical question could be, what about kids? I mean, not even mental disabilities or physical, but just such a big sample as just kids. Maybe they cannot read the message. That's why I also try to stay away from things which do not work. That's a good case today is brake lights. They work everywhere because, well, most people can see them well and respond to them well. And then there are a couple of other concepts, for example, V2X, where we are looking into equipping people with more, like, for example, tactile feedback in case of a car coming, maybe if they're blind or they cannot hear a car coming. And another one is big one is these days is the focus of this kind of research on aging population. So we in Europe, and it's another issue which we are facing, like, for example, Asia. But in Europe, it's also interesting. Well, not interesting, but it's required to also think about how people with dementia, for example, and more older folk can interact safely with such cars. I'm not giving you like micro scale answers to what exactly needs to be done, but I'm saying to you that I'm involved a bit myself, and it's definitely a prominent field of research today as well on this kind of issue. I hope it answers a bit your question.
Thank you for your answer. I also have a question about the experimental setup. So now I can see your experiment was conducted in the virtual environment, and I guess that maybe the next step in the future will be the real on-site experiment. And I can see there are many like challenges like the weather or the light conditions. And in general, how do you design your experiment when you are thinking about this virtual environment to the physical environment?
That's also another very good question. I also, a little bit backstory, also used to work in Göteborg for a few months in Volvo trucks. For example, there I did on-road experiments where we had a bunch of truck drivers driving around Sweden for 2 weeks with some systems which we were working on. That also exists. There are a couple of things. So it's much more complicated to make it work. It's way more realistic indeed, but sometimes you don't need such realism. For example, now we're doing this crowdsourced eye tracking experiment with some basic stimuli to understand what it means on a grand scale scheme of things before we go in on the field and maybe making some on-road study with truck drivers in Göteborg. You also mentioned weather and light conditions and all that. It's also a good one. I know from some news stories that some companies came to Sweden, some Kiruna somewhere, to test the AI systems from California. They surprisingly they did not work because of snow. So there are a lot of, but in my own field, because there are thousands of people around the world literally who are working on this. We are now trying to offer our service by means of accepting what works through sensor work and assuming hardware kind of works. And then we offer our ideas on how that work in hardware. Maybe it's working 20 years from now, maybe it's not working yet, but we are now trying to think how that hardware could be used for when humans and in the case of a scenario. And when humans are involved, 90% of research is done like what to do by the simulators, because it's just with cars is dangerous essentially to have people inside next to the car. Yeah, I can talk about this forever, but that's maybe in a few words a little bit what you addresses what you asked.
Yeah, thank you for your answer. I think we have like a time for one more question if there is any question. Maybe Rafael, yeah.
Thanks, Pavlo, for the presentation.
Thank you.
I was wondering if you did experiments with like more than one pedestrians, and in a scenario where, let's say, we are in a crowded crossing, and sometimes, let's say, people just arrived from the metro station, is crossing the line, and there is a bus waiting for passing, and also full of people, and sometimes the bus ignores the glaze to be able to have the flow of the traffic, and then the pedestrian needs to wait until the bus to stop. Have you did any experiments on this kind of more, let's say, in a crowded environment?
That's a good question. I will drop a link in chat. That's another hater of mine. It's not about the crossing situation, but I was in Japan the other day working with Nissan. I did an experiment on how multiple people can react to a car driving different ways. One way was a more robotic trajectory, which is more scripted, and the other way was more human-like way of driving. So we also tried to see group effects. At the very moment, I'm running one study as well with exactly that. So we have multiple people trying to cross the zebra crossing in front of an automated vehicle. Some things are going on, but it's a kind of a point of what I'm doing. So at the moment, most of the research is one pedestrian and one car. And I'm now trying to look into indeed what happens when there are multiple pedestrians. We are now looking into one study at how distance between pedestrians matters. So we basically control distance between two people in the same world. And then we're trying to see how, if a person is far away from you, or if they're on the other side of the road, or if they're close to you, how it affects your own crossing decisions. So you're making some baby steps towards understanding how it works in the future as well.
Interesting, thank you.
Yeah, I just have a small question. So since I'm working with the production logistics and there are lots of like mobile robots and many operators are moving around. So I think it's quite similar situation. And have you contacted or worked together with the industrial setup as well?
Good question as well. So the couple simulator is not called couple simulator for traffic research, but it's called couple simulator. Also, one of my ideas was that an agent can be anything. So yeah, I have a colleague who is working with robotics, social robotics. So she's doing things with robots. And we are now thinking of a study where essentially we swap a car with a robot and we do similar things, but also inside of the house, in the inside environment. I have not directly been involved with research with logistics. Tarun is my bigger thing to that. Maybe it will happen in the future. But yes, that's also a good question. I think like that's in my view, in general, because we have technology which is now free for the most case, so you can clone the repo on GitHub and just get it working. I think in many fields like logistics, we can now step up and do multi-agent research as well in the future.
Yeah,
I hope
that
it
will be
answered the
maybe
question.
good collaboration in the future together.
Yeah, why not?
Yeah. So I think time is up, and thank you for the good presentation and fruitful discussion as well. So I hope
Thank you
everyone
for your
enjoyed our seminar.
invitation.
Yep, thank you very much.
Thank you. Bye.
Have a good day. Bye-bye.
Yep, have a nice day. Bye bye.